Hi everyone, my name is Anthony and this is my Physics 2111 lab. This is my table of contents. So for this lab, the purpose was one, to visualize how Newton's second law applies to real world objects, and two, to verify experimentally that Newton's second law is true in practice. Specifically, we wanted to visualize an object moving with constant velocity. To do this, we used two modeling tools, Tracker and GlowScript. Tracker is a video analysis software, and GlowScript is a computational modeling program, and both of them can give position and velocity data. This lab is based on the fundamental physical principle of Newton's second law and the kinematic equations for position and velocity. Throughout this presentation, I will reference the position update formula, velocity update formula, and Newton's second law, which I have shown. Our prediction was that the data from Tracker and the predictions from GlowScript should align, which would show that Newton's second law does describe the motion of an object. However, as you'll later see, the real-life experiment data and the computational data do not match perfectly, and this is largely due to limitations in the experiment setup and data collection. And I'll explain this in the sources of error at the end. So for this lab, we defined the system as an expo marker and the surroundings as the table's surface and the air. Since air resistance or friction are difficult to measure and are relatively small, we're going to assume that these forces are negligible. For the initial conditions, in the y direction, the net force is 0 because gravity and the normal force from the table cancel out. And in the x direction, there's an initial applied force to start the marker rolling. However, because we want to analyze constant velocity, meaning that the net force is 0, we're going to only analyze the marker in the middle of its motion. At the beginning, the applied force is going to increase velocity, and at the end, friction will start slowing it down. So by only looking at the middle portion, we can assume that there's no net force. Now for the experiment data, I'll explain Tracker. So Tracker uses a reference and a set of axes. Our reference in this case is the length of the marker, which is the blue bar, and the axes are the magenta bars. And the red squares represent where I click the center of mass, and that's how Tracker works. By using the centers of mass, it could track the motion of the object. On the right is a screenshot of our video, and on the left, you can see our Tracker data. This is our computational data. The middle is a picture of our code. On the right is the actual output, and on the left is an equation that I use for our code. So in my code, the initial position and the initial velocity are from Tracker. So the initial position is just when time is 0, and the velocity, I took the first two outputs from Tracker and calculated the velocity, and velocity is equal to delta x over delta t. And so by using the first two entries from Tracker, I could calculate velocity. And then our delta t is just equal to the frame rate, which we get from Tracker. And for me, it was 0.033 seconds. And for the code, we used a while loop to continuously update the position and velocity formulas. In the loop, we set force is equal to 0 because, as we said, we want constant velocity, which is when force is 0. And we said, and we want to, and line 64 is important because we want to continuously update the time, which will continuously repeat the loop. And we do this until the time is greater than or equal to 1.267, which is the end of our data. Now to compare the two data. So the blue line is a perfectly linear line, and that represents our model data. It's our model data because it's perfectly straight, which means there's no errors, and then the force is exactly 0. However, looking at the red line, which is our real observed experimental data, you can see that around 0.25 seconds, it starts to deviate from the blue line. And that just represents how the marker is slowing down if the net force is no longer 0. For some similarities, both lines are moving in the positive, both have positive slopes, which means it's moving in the positive x direction. And the difference is that the red line does not have a net force of 0 for the entirety of the experiment. Now for the conclusion. So first I'll talk about the sources of error. The most obvious source of error is that we cannot completely ignore friction and air resistance. These forces are always present in real life and eventually will have an effect on the marker. Another source of error is that the marker's center of mass is kind of weird, which makes it difficult to roll perfectly straight. While Tracker allows us to customize the axes, if the marker doesn't roll straight, then our data will be off. We could have used rails to guide the marker, but that would also introduce additional friction, which would also lead to more error. The last source of error that could be possible is that human error in Tracker. So for Tracker, we must manually select the center of the marker for each frame, but it's impossible to click the exact same spot every time. So as you can see in our Tracker data for the Y positions, they aren't the exact same, which represents how I'm not clicking the exact same spot, and this will shift our data. Now for the what if and what does it mean? So if I were to flip the axes so that positive x and negative x were interchanged, the magnitudes of the velocity, position, and force would be the same. So that means the slope would be the same. However, the direction is reversed. So therefore, the graph will start at 0 and point in the negative direction. And then for what does it mean? In the real experiment, there are four forces that could act on the marker: gravity, the normal force, air resistance, and friction. However, gravity and normal force will cancel each other out, and air resistance or friction are so small that we're just going to ignore them. Thank you.